Om Swastiastu. Hello everyone. My name is Samuel Benaya Batubara with student ID 22055311097. In this video, I will explain about metal casting, design, material and economics from chapter 12 of the book Manufacturing Engineering and Technology 6th edition. Metal casting involves controlling many variables such as metal flow, mold design, and cooling rates. This factor determine the quality of the final product. In this chapter, we will discuss how good design and material selection improve casting performance and reduce production cost. Design principles in casting have evolved through years of experience and simulation studies. The key idea is to design shapes that are easy to cast, select suitable material, and properly locate parting lines, gates, and risers to ensure smooth metal flow and solidification. Sharp corners, uneven wall thickness, and flat surface often cause stress or defect. To avoid this, designers use fillets, uniform section, and proper draft angles. Shrink edge and machining allowance must also be considered. Figure 12.1 and 12.2 illustrate examples of poor and good casting designs. This table 12.1 lists the normal shrink edge allowance for various metal casts in sand molds. It shows how different metals contract during solidification, which must be considered when designing casting patterns. In expandable mold process, such as sand or investment casting, the goal is to achieve uniform solidification. Risers play a key role. They must stay molten longer than the casting to fit metal and avoid shrink edge cavities. The mold layout and riser placement are crucial for quality. This figure compares poor and good casting designs. The good example shows smoother shapes, proper radius, and uniform section, all of which help reduce defect and improve die life. Permanent molds and die casting require small draft angles and precise dimensions. This process usually produces near net shape parts with smooth surface and minimal finishing. Figure 12.3 shows example of poor and improved die casting designs. Today, computer simulation tools such as Microsoft and Procast allow engineers to model metal flow, temperature, and solidification. These tools help predict defects, optimize gating systems, and improve both quality and productivity. Casting alloys are divided into non-ferrous and ferrous types. Gray iron is the most common by tonnage, followed by ductile iron, aluminum, zinc, and magnesium. Alloy choice depends on desired strength, machinability, corrosion resistance, and cost. Figure 12.4 compares the mechanical properties of various cast alloys, including steels, iron, and non-ferrous metal. It shows that properties like strength, ductility, and hardness vary widely, even within the same alloy group. Cast steel, in particular, display the largest variation, reflecting their diverse composition and heat treatments. Aluminum and magnesium alloys are widely used in automotive components due to their low weight and corrosion resistance. Copper-based alloys are used for bearings and electrical parts. Zinc, tin, and lead alloys are ideal for die casting or bearing surface. High-temperature alloys serve aerospace and turbine application. This table shows typical application and characteristic of various casting alloys. It compares their castability, weldability, and machinability. helping engineers choose the most suitable material for its product. Ferrous alloys include several types of cast iron and steels. Gray iron offers good machinability, ductile iron provides high toughness, and white iron gives wear resistance. Malleable and compacted graphite irons bridge the gap between strength and castability. Cast steels and stainless steels are used for high-strength industrial components. This table summarizes the mechanical properties and common use of different types of cast irons. Each type, gray, ductile, malleable, and white iron, has unique strength and application from engine blocks to heavy-duty gears. Table 12.4 presents the mechanical properties of different classes of gray cast irons. As the class number increases, tensile strength, hardness, and elastic modulus also rise. This shows that higher grade gray irons provide better strength and wear resistance for heavy-duty application. Table 12.5 summarizes the mechanical properties and typical use of non-ferrous cast alloys such as aluminum, copper, and magnesium. It highlights how different alloys offer unique combination of strength, ductility, and corrosion resistance for applications like engine parts, valves, and marine components. Casting irons depend on the materials, molds, equipment, labor, and production rate. Sand casting is inexpensive for small batches, while die casting and investment casting become economical only for high production volumes. Table 12.6 shows the relationship between cost and production rate. In summary, good casting design reduces defects, alloy selection determines performance, and cost analysis ensure economic efficiency. Computer modeling further enhances quality control and productivity. The material for this presentation were fully adapted from Chapter 12 of Kalpakjian and Smith Manufacturing Process for Engineering Materials. And that is all of my presentation. Thank you for watching. Om Santi Santi Santi.